Welcome to this monthly seminar of PIST. Today I have the pleasure to present you Michalis Skotiniotis from Universidad de Granada and Instituto Carlos I de Física Teórica y Computacional, who will present us a talk entitled Symmetry in Quantum Information from Protocols to Foundations. Michalis completed his undergraduate studies in Bristol, UK, and then moved to Calgary, Canada, to complete his master and also his PhD thesis. And then he moved to Innsbruck, and he obtained a Juan de la Cierva position in Barcelona, and he's currently with Ramón y Cajal in Granada. His main interests are metrology, open quantum systems, quantum computation, foundations, etc. So, Michalis, your turn.
Thanks, Alvaro, and thanks for the invitation. It's a pleasure to give this seminar. I hardly get to talk to generally PhD students, so it's nice, even though I see that there's more than PhD students in the audience. In particular, my former boss, John, is in the audience. Thanks for coming. So yeah, before I start, I guess just to give you an incentive or a motivation of why I made the talk, I have oh, yes. I was wondering if anyone knows who this gentleman is. If anyone does, then please shout out. If not, then so he's not a physicist. In fact, as far as I know, he's not a scientist. He was a very famous architect. His name is Ludwig Mies van der Rohe. And the reason why I'm presenting Mr. van der Rohe is for the following. So this is some of the buildings that he has built. Please pay attention to the architecture. So this is the National Gallery in Berlin. This is the Seagram building in New York City. He's also very famously designed the IBM Plaza in Chicago. Perhaps his most famous building is the following one, is Farnsworth House, also in Chicago. And something which I know very well, and maybe a lot of people in Spain may know, is that he's also designed the pavilion in Barcelona. So I don't know if you notice the buildings of this gentleman. You will notice that they have a high degree of symmetry, which is very strange when one finds that Mr. van der Rohe is responsible for uttering the following statement. Apparently, he had said that symmetry is but aesthetics for fools. So as a person who works a lot in symmetry, when I first encountered this statement, I was very irked, I have to say. So part of the talk today is just to provide maybe a response to Mr. van der Rohe, who unfortunately is not with us to see it, but this is just a way to showcase a little bit the use of symmetry in physics, and in particular in quantum information. So this is an outline of my talk. I'll start first of all with just a very simple example of how we use, or rather how symmetry is implied in quantum information, but we never hardly use it in a very clever way. And then I'll talk a little bit about what I like to distinguish between quantum theory and quantum physics. Then I'll talk a little bit about the mathematics of how we deal with symmetries within the quantum formalism, and in particular about representations and this very famous theorem by Schur-Weil. And then I'll just give you a flavor of a couple of things that we can use symmetry to do. The first thing will be from the very origins of dealing with symmetry in quantum information, which is called the resource theory of asymmetry. Then I'll talk about how we can do quantum information under symmetry constraints. And then I'll jump a little bit ship, and I'll talk about how to use symmetries in performing ultra-precise quantum measurements. And finally, how we can use symmetries to tackle some of the foundational problems in quantum theory. So here's a guiding example. This is, I think, something that probably every one of us that has ever done physics has actually looked. So the problem is very simple. You imagine that you have an atom, which is, for the moment, the only two energy levels that are really at play is the ground state of the atom and the excited state. And you have a pair of detectors here on the right. And then what happens now is that you say, consider that the atom is prepared in one of two following states. So it's an equal superposition of the ground state and the excited state. The only difference is the phase. One of them is a plus and the other one is a minus. Okay. And what you want to do is to distinguish in which of these two states the atom is in. So this is a very simple problem. These two states are orthogonal. In fact, you can define them as they are the eigenstates of the observable sigma x. So naturally, you can distinguish them. You can just perform this measurement, and you can tell with certainty in which state the atom is in. However, there's a bit of a problem, because in your lab, technically, and as far as we know in the entire universe, there is the principle of conservation of energy, which means that in any closed system, the only operations that we're allowed to perform are those that commute with the Hamiltonian of the system. And in this case, the Hamiltonian of the system is in the sigma z, it's in this basis, in the ground excited basis. And in these two, the sigma x observable and sigma z do not commute, which means that this measurement is, if you were able to perform it, would be in clear violation of energy conservation. But then again, experimentalists make these measurements all the time in their lab. So how is this possible? Obviously, they're not violating the conservation of energy. So what is really going on? Well, actually, if you look at how people do this measurement, is that they introduce an auxiliary system. In this case, it's a laser, and this laser is prepared in some coherent state. And then what happens is that you have a total energy preserving interaction given by this Hamiltonian here, which many of you will recognize as a version of the James-Cummings Hamiltonian. Okay, so you engineer an interaction between your laser and the atom, and you turn this interaction on for a certain amount of time. You pick this time very, very carefully. And then you can show that the average fidelity between you performing the measurement corresponding to sigma x and the measurement that corresponds with you starting, let's say, with the eigen basis of sigma z, okay? This average fidelity has this number here below. It's 1 minus this constant, and this alpha squared is the average energy in the laser. So clearly, if your laser has a lot of energy, it's huge energy, then the fidelity here is 1, okay? So you can perform this measurement almost with certainty. The key thing here is that the only reason why you're allowed to perform this measurement is because you have access to this laser, in particular, this system here, okay? And this state is going to be very important for what we're going to talk about next, okay? So let me first talk about quantum theory and quantum physics, because this is an important distinction between the two. So for me, quantum theory is essentially the following 3 axioms. This is all of quantum theory, excluding relativistic effects. If you want to understand the mathematical formalism, this is it in all its glory, okay? There is nothing more. There are 3 axioms. The first one tells you what the objects of interest of the theory are. These are positive semi-definite operators with unit trace. The second one tells you how to compose the different objects of interest. In quantum theory, we do this via the tensor product. And the third axiom tells you how to interconvert between objects of the theory. And in general, in quantum theory, this is accomplished by something called a completely positive trace non-increasing map. This is just a map that takes density operators to density operators. It is linear, and it has to satisfy the following 2 conditions. Its trace is non-increasing. You cannot increase the trace of a density matrix using these operations. And complete positivity is essentially this condition here. If I have an auxiliary system and I do something on one part of it, then the resulting system is a valid quantum state. Okay, and that's it. So what about, just to make it clear about this axiom 3, because you may be wondering where are measurements and where are unitaries. So unitary evolution is one particular instance of what's known as a completely positive trace preserving map, okay, which is given by this form here. You may recognize this as sort of the Heisenberg picture. And projective measurements are given by this kind of map here. These PK are just projectors, okay? So this in particular, this form here corresponds to you performing a measurement, but you haven't looked at what the outcome is yet. If you actually look at the outcome now, so you figure out the label K, this is what's known as a fine graining, then your CPTP map is essentially this object here, which you can normalize in this way. Okay, so you have the probability of getting outcome K and the post-measurement state. And the beauty of this formalism is that it allows us to include more general things. For example, generalized measurements of what people call positive operator value measures, or quantum instruments. These are objects where you just have a set of positive operators that sum up to the identity. Okay? Now, what is quantum physics? In quantum physics, the objects of interest, i.e. density matrices, provide a description of what in physics we call elements of physical reality. So it's the position of a particle, or the momentum of a particle, or the energy of a particle, or I don't know, the polarization of a photon, things like this. And completely positive trace non-increasing maps describe physical processes, things like interactions, measurements, these kind of things. Okay. Now, how do you tie these two formalisms together? Well, physical quantities, at least in the physical formulation of the theory, we said that these physical quantities correspond to Hermitian operators. And the problem we have with the general formalism is that not every Hermitian operator corresponds to a physical quantity. Okay. And the other thing is that physical quantities are subject to additional constraints. They're subject to conservation laws. And the mathematical formalism of quantum theory says nothing about conservation laws. So you can think of let's say, quantum physics as the same idea that Plato had in his cave. You have the abstract formalism, and what quantum physics is you're projecting the shadow of this formalism on the physical world. But when you do this, you're including along for the ride additional things that aren't present in the original formalism. And these things are going to be precisely the things that we're going to be interested in. Conservation laws and how they play a role in defining different tasks within quantum information theory. So what's the importance of conservation laws? Well, we know, for example, one of the most celebrated theorems in physics is Noether's theorem, that the existence of a symmetry implies a conservation law. So if we have time invariance, we have conservation of energy, and so on and so forth. We have several other fundamental conservation laws, like charge parity time inversion symmetry, or Lorentz symmetry, or chirality. And we even have things like the behavior of systems that are bosons or fermions. All these stem from symmetry arguments. Okay. So now that we've talked about the symmetry and its importance in physics, then the next question is, okay, how do we incorporate this formalism within the framework of quantum theory? And this is done by what is colloquially known as group theory, or more specifically, group representation theory. So let's assume that we have an object of interest, a density matrix that is a linear operator on some d-dimensional Hilbert space. And let's assume that we have closed system evolution, i.e. the evolution is described by Schrodinger's equation. Okay, mathematically, this means that we describe this by a unitary matrix with determinant 1. Okay, now if you consider the set of all these matrices together, they form a group under matrix multiplication. And in fact, this is they form what is known as a unitary representation of the special unitary group on d dimensions. Okay, so all rotations that you can do in d dimensions. Okay, now if we're going to talk about representations mathematically, these are basically homomorphisms of a group onto a set of matrices, and we say that a unitary representation is reducible if there exists a subspace of the Hilbert space that's not trivial, i.e. it's not the empty space, such that for all vectors in this subspace, every time I multiply with any element of the unitary group, I stay within this subspace. Okay? Otherwise, if this is not the case, then the representation is called irreducible. Okay? Now, the importance of reducible and irreducible representations, you can think of them as irreducible representations are to representation theory what the prime numbers are to number theory. If you give me any representation, particularly unitary representation, I can always decompose it into these irreducible representations in a very specific way. Okay? So the two things that are important with regards to these irreducible representations are known as Shor's lemmas. The first one tells you that if you have an irreducible representation and you have some linear operator A that commutes with every element of this irreducible representation, then the only matrix that can achieve this is a multiple of the identity. And the second lemma tells you that if you have two irreducible representations, here I call them U and V, And then you also have a linear operator A, such that when you multiply A on the right by U, you get the same answer as if you multiply A on the left by V. And this occurs for all elements of the group. Then either this matrix A is 0 or U and V are equivalent representations. In other words, U and V are related by a basis change, and this basis change is given by A and A inverse, okay? The other important thing to note is that two irreducible representations that are inequivalent, they have an orthogonality relation. You may recognize this, for example, if you're a physicist, then this would be the case for example, the spherical harmonics or the Fourier basis, for example. If I give you two irreps and I integrate over the elements of the group, then what I get is an orthonormal basis. Okay, that's just the mathematics, just very briefly. Now, what does this all mean? It means that when I give you a representation of a group, since this representation acts on a Hilbert space, if it is reducible, it means that there exists a basis in which this representation can be written in block diagonal form. In other words, I can write this matrix as a sum of all the irreducibles, and some of these irreducibles are going to appear more than one time. This is what's given here, okay? And equivalently, instead of writing it like this, I can introduce an identity, a virtual tensor product here, and this identity has the dimension of the number of times the irreducible representation corresponding to lambda appears in the composite. Okay? There's always a basis that does this. But if there is a basis that allows you to write U in this way, then you can think of your Hilbert space, since the U is acting on it, under the same basis that it also block diagonalizes in a similar fashion. In other words, your Hilbert space will decompose into blocks. Each block is labeled by the irrep labeled lambda. Okay, and inside each block, I can construct a virtual tensor product of two different subspaces. The first one we call the carrier space. If you come from high energy physics, you may know this as the nuclear spaces. And the second space here is called the multiplicity space or the color space. What's the significance of this? The space here, the carrier space, is the space upon which the irreducible representation U lambda acts. And this space N lambda is a space on which this irreducible representation acts trivially, i.e. it acts like the identity on it. Okay? Now, this is, so far, I just talked about a single Hilbert space. Now you may think, okay, what happens if I have several Hilbert spaces on the composition? Well, these two, if you have this situation, then you naturally have the action of two different groups. The first one is the one that we've been talking about. It's the group of special unitary matrices of d dimensions, which acts in this way. It's the same unitary on every system. And the second one is the group of permutations. Okay, so I take this, I have a tensor product, and I can permute the Hilbert spaces in any way I want. Okay, and very naturally, the actions of these two groups commute. Okay, which is very handy because both of these groups individually can be decomposed into their irreps. It means I can write the Hilbert space in block diagonal form, either for one group or the other. But the fact that they commute is very important. And this is a famous result known by, derived by Schur and Weil, which tells you that the blocks of this tensor product under the action of the two groups are in one-to-one correspondence. This means that I can either use the irrep labels of SUD to label my blocks or the ones of the permutations to label my blocks. A very famous example of this is when you have two spin-half particles. You know that when you have two spin-half particles, you can decompose the total Hilbert space in two subspaces. One of them is called a Hilbert space that has total angular momentum equal to 1, and the other one is the one that has total angular momentum equal to 0. But you may also know these two spaces as the singlet and the triplet subspaces, because the singlet gets a phase every time I exchange the particles, whereas any state in the triplet gets no phase when I exchange the particles. That's exactly the content of Schur-Weil duality. Okay, so I can either label the subspaces either by their total angular momentum, which in this case is the irreducible label for SU2, or by their permutation properties, which is the irrep label for S. Okay, now In this context, when we have a multiple spaces, there is a very nice way of understanding the action of each group in terms of this virtual tensor product. If you remember, these two groups commute. So in this, with respect to this basis, the action of SUD is happening on this space here, on the carrier space of ML, and the action of SU of SN happens in this space here. So they act on different subspaces in this way, and this is why they commute. Good. So now that we've had the mathematical framework, let's talk about the use of reference frames within the quantum formalism. Okay, so symmetry groups we know correspond to transformations of a particular frame of reference. For example, if we talk about rotations, the rotational symmetry, then we're talking about a Cartesian frame of reference. If we talk about translations, we're talking about a positional frame of reference, and so on and so forth. So what I'm going to talk about here is much more general. Let G be any symmetry group, and you know its action on the Hilbert space is given by some unitary representation. Then the question you want to ask is, okay, what states are free under this restriction? Okay, I have a symmetry group, which means I have a conservation law. What states can I prepare under such a conservation law? The answer is you can prepare any state rho that commutes with all the elements of the unitary representation. And similarly, the things that you can do for free, your free operations, are any operator that commutes with every element of the representation. Okay? Any state or operation that does not satisfy these two constraints is called a resource. And it's a resource because it allows you to overcome the restrictions imposed by symmetry. And here's an example, back to our guiding example. So the conjugate quantity to energy is phase. Okay, so now if you consider the unitary operator that we had before with the Hamiltonian, this you can write in this very in this basis here, where n is the number of excitations. Okay, and your free states are those that can be prepared without access to a phase reference, right? Because under u theta, this u theta corresponds to basically an oscillator, and theta is the phase of this oscillator. If you do not have any such oscillator, the only thing that you can prepare are states that are diagonal in the energy basis. Okay, and your free operations are those that can be performed without access to a phase reference. So if you want to think more operationally, a phase reference is a clock. If you don't have a clock, the only things you can do are things that don't depend on the relative on the time, for example. Okay, so this condition here imposes a constraint on the operations that you can do without having access to this phase reference. By the way, this K and beta here, for those of you who know, is that every CPTB map can be written in terms of its cross operators. The restriction of not having a phase reference implies that all your cross operators can be written in this very special form. Essentially, what you can do is you can remove energy, you can add energy, or you can change the relative weights of states that are superpositions in energy, and you cannot do anything else. That is it. So if you look at this, these are your free states and free operations, then now it starts to become more clear what the purpose of this phase reference of this coherent state is. Well, this state here does not meet the constraint. It is a resource. Okay? So now you can ask, okay, if I'm under a conservation law, how best do I capture the notion of what a resource is? How do I quantify which states are more resourceful than others? What is the operational meaning of such resources? Okay, what can they allow me to do? Okay, and how can I rank them? What states are optimal resources for different groups? How do we interconvert between different resources? These are all the questions that the resource theory of asymmetry deals with. If you want to, the analog of this is you can think of the restrictions under a symmetry group as the same thing as talking about entanglement under local operations and classical communication. If people are restricted to doing only local operations and communicate classically, then having entanglement is a resource that allows them to circumvent this restriction. So by the same logic here, what you do is you say my restrictions are now operations that commute with all the unitary representation of some group. And I'm asking what are the states that allow me to circumvent this restriction. And resource theories for asymmetry have been constructed in several different contexts. One is for energy, there's one for angular momentum, there's also one for charge parity time that you can find. They're very nice and they're very handy because they have a very rigorous mathematical definition and we can work with them very efficiently. Okay, so how do we use such symmetry constraints? What is the operational significance of such symmetry constraints? Well, consider having two parties, Alice and Bob. Okay, and Alice has her Cartesian frame of reference and Bob has his Cartesian frame of reference. And Alice prepares a state relative to her frame of reference. And now what Alice wants to do, this state encodes some information, classical or quantum, and she wants to send this state to Bob. Okay, so if she sends the state to Bob, since Bob's frame of reference is not the same as Alice, if Bob knew the relationship between the two reference frames, then he would describe the state in this way here. However, if Bob has no knowledge of the relationship between his and Alice's frame of reference, then Bob is forced to average over all possible relations. Here, I assume the group to be discrete. If it's continuous, then you would replace this with an integral and the uniform measure over the group. Okay? Well, this state here is very special because it will destroy all coherences between different invariant quantities present in this state. In particular, because of this unitary, you will impose this block diagonal structure, and this state sigma will be block diagonal in these irrev spaces, okay? So if you do not know the reference frame relative to which your communicating partner has prepared a state, then you cannot communicate whatsoever because you have no frame of reference. So lacking a shared frame of reference for some degree of freedom is equivalent to a noisy communication channel. You can think of the same scenario we had before, only this time Alice and Bob have exactly the same frame of reference, but then somebody comes and changes the orientation of the state, and you do not know in which way they changed it, okay? Now, the state at Bob's end, in terms of the block diagonal basis here, can be described in this fashion here, okay? And you notice that this is the part of the state that lives on the action of our group, and this is the part of the state that lives in the multiplicities. So if Alice and Bob want to communicate classical information, the way that Alice does it is she encodes this information in the irrev labels lambda. In other words, she manipulates this probability distribution here to send classical information to Bob. If she wants to send quantum information to Bob, then she has to manipulate these states here. Okay? And what do these things correspond to? Well, the irrev labels here, they correspond to absolute quantities, things like the total energy or the total angular momentum. You would use these degrees of freedom to communicate classically. And these things here, they correspond to relative degrees of freedom. In other words, if you want to communicate quantum information here, what you would do is you would encode the information in two states and in the relationship between the two states. So for example, if we're thinking about, let's say, spins, if I prepare two spins at a given angle and both spins undergo some rotation I do not know, the relative angle between these two spins remains invariant. And that's where you put your quantum information. Okay, now these all may look very hypothetical and you may be wondering, okay, well, where do these communication channels crop up? Actually, they crop up everywhere. So for example, these collective noise channels, they could be phase diffusion in optical fibers, or they could be neutral atoms in some ion trap, and then the ion trap has a global magnetic field going through it that you do not know. Okay, both of these situations are very realistic. Both of these occur in labs. Both of them are described by these collective noise models, and you can treat them as if you're lacking some relevant reference frame. Okay, in a similar fashion, you can also use this symmetry to construct error correcting codes. So remember, if I were to go back, remember I told you that this space here is immune to the action of the of the representation here? Well, if you think of this as a communication channel, and your communication channel has some form of an error, then all that it affects are the degrees of freedom here. These degrees of freedom remain unaffected. So you can use these subspaces to protect your quantum information against this kind of error. And indeed, such error correcting codes have been constructed in several ways. You may know them as decoherence-free subspaces or decoherence-free codes, and they use exactly this idea. Okay, now let me tell you about another way that you can use the symmetry to do some very, very cool stuff in quantum information. So you all know that quantum states cannot be copied. There exists no machine that for any state I give you, it produces 2 copies. But it is known that certain subsets of states can be super replicated. What do I mean by super replicated is I give you n copies of some state, and I demand that what you output is a state of m copies that is very close to the original state tensor m, okay? So they need to have very high fidelity, okay? Now, deterministic superreplication is known not to exist, okay? But a probabilistic protocol does exist if you restrict the set of states that you want to superreplicate. For example, one famous case, these states here, which are very famous for, they play a very crucial role in Ram's interferometry or in atomic clocks. So imagine I give you n copies of this state, and I ask you to produce for me a state that is very close to m copies of this state. Well, such a protocol exists, and in fact, this m is of order n squared. Okay, and this is exactly what superreplication is, that I give you quadratically many copies with high fidelity. And the protocol that achieves this exploits this this symmetry interface to construct essentially what is known as a probabilistic filter. And all it does is essentially this. It just projects on this filter. If it succeeds, then you know you have the state you want. The problem is that it succeeds with a probability that scales exponentially bad with n. The more copies you ask me to produce, the lower this probability that I want to release. But what about, okay, that's for states. Now let's think about trying to copy or superreplicate unitary gates. Okay, so suppose that I give you n copies, n uses of some gate u theta, and I ask you to produce some other gate, which is to very high fidelity, close to m uses of the same gate, where m is bigger than n. Okay, and the gates I'm going to focus on now are phase gates. So they have this very particular, very nice structure. Okay, well, it turns out that this we can do, and we can do it deterministically. And what is the point? The point is that if you remember, if I take the tensor product of this gate and I use the symmetry properties and I can decompose it, it turns out, because the gate is of this form, that the spaces where the representation acts irreducibly are one-dimensional, and they correspond to, let's say, the number of energy sectors you have, or the number of energy, the total energy that your string has. Okay, and the multiplicities, they scale using a binomial distribution. So here I plotted them, for example, for you. For example, here it's all the energy sectors, the different m's. Okay, and here is the number of copies of each representation that I get. So what is the idea? The idea is, if you notice, this is a Gaussian, and it makes no sense for me to copy faithfully things that don't occur very frequently. It makes more sense for me to copy what are the typical sequences in these strings. And indeed, if you just focus on copying the bulk or what the typical subspace of this problem, then what you end up getting is a gate that faithfully has a fidelity, or very faithfully has very high fidelity with this gate tensor m, and the m you get is n squared. So to put it, let's say in a context that we'll understand, currently IBM asks me to pay for every gate I use. So what I do is I pay 100 euros to use, let's say, 100 times the gate. But what I can do with this protocol is I can pay 100 euros and use the gate 10,000 times. So it saves me money. Okay? Good. So I should mention that this super replication protocol doesn't just work for these special gates. It works for all unitaries, in particular for SU2. Okay. And there is an experimental proof of principle experiment that demonstrates that it actually did work. Okay. And it's done using photons. And notice that every time it's the same trick. It's this sure-while duality. Decompose things into the space where the representation acts and the space where the permutations act. And depending on what is the task, to protect the information or to copy the information, you exploit these symmetries in a certain way to accomplish what you want. And similar techniques are used for compressing quantum states. So I'll give you n copies of a state, and I ask you to store them in a register that is smaller, just like we do when we zip classical data, or whether we can probabilistically store and retrieve quantum gates, or exponential compression of quantum gates, for example. So large gates that I want to compress into a smaller register. So I can do, for example, faithful quantum simulation. All these protocols exist, and all of them use exactly the same thing. Good. So that's everything I wanted to say about, let's say, using symmetry in quantum information protocols. Now let's go see how to use symmetry in ultra-precise measurements. So I don't know how much people know about metrology, so I'll start from the beginning. What is the quantum metrology? Is essentially a statistical inference problem. Okay, I give you a probe. You send this probe through some dynamical process, which depends on some parameter lambda or set of parameters lambda. And then I perform measurements on this probe to extract some probability distribution. And then I analyze the probability distribution to try to learn something about these parameters lambda. Okay. So in principle, what I do, this is the standard statistical inference problem. I have a random variable here, x, which is distributed according to this distribution here. I construct an estimator, okay, I sample from this distribution. From the samples, I construct an estimator, okay? And then what I want from my estimator is two things. I want it to be unbiased. On average, it should give me the real value of the parameter. And I want its precision to be the error to be the smallest possible, so highest precision, okay? So there's a very famous theorem that gives us lower bounds on the precision of any such unbiased estimator. It's called the Kramer-Rao bound, okay, where this F here is the Fisher information. It's given exactly in this form here, okay? And in the Kramer-Rao bound has the additional bonus that it also tells you what is the estimator that achieves it, at least asymptotically, and it's no surprise, it's always the maximum likelihood estimator. So there's a quantum version of this. Okay, the only thing that you have to change is to realize that instead of this probability distribution, which is classical, in quantum theory, this probability distribution is generated by some measurement on some state. Okay, and since in quantum theory, we are allowed to perform any measurement whose operators are positive and sum up to the identity, then you can, the maximizing over all these possible measurements gives rise to what's known as the quantum Kramer-Rao bound. And this calligraphic F is the quantum Fisher information matrix. Okay. So let me just take you through a couple of problems where I personally use at least these symmetry arguments. So the first one has to do with imaging of two-point sources. So we all know, for example, from a century ago, that two-point sources can barely be resolved if the maximum of intensity of one source on our image plane is exactly on top of the minimum of the intensity of the other. This is what the Rayleigh criterion tells us. Mathematically, it corresponds to this angular resolution of your optical device. Okay? Or in more modern terms, normally it's phrased as a signal-to-noise ratio. Okay, so you want the minimal resolvable distance is the 1, such that this SNR here is bigger than or equal to 1. Okay, now what happens is we're going to make two assumptions. We're imaging things that are very, very far away. So we're in the paraxial approximation. And now what we're going to do is we're going to assume that our sources are quantum. So they produce monochromatic light, and they're very faint in the sense that most of the times what I get is nothing. And some of the times I get some state rho 1. And this state rho 1 is a mixture of my 2-point sources, one source located here, let's say on the left, this dotted one, oh, sorry, this one, or this one here, okay? So you can compute the Cramer-Rao inequality in this case as well. If, in particular, you can fix your measurement and compute what is the precision of this measurement. So the classical Rayleigh limit corresponds to if you just measure the intensity of what you see on the screen. And if you do this and you compute the efficient information matrix, for the separation of the two sources, you get this factor here, okay? And you notice that as D goes to 0, this factor goes to 0. The precision is the inverse of the Fisher, so your precision blows up. And this is indeed this is the mathematical explanation of the Rayleigh limit, okay? But in quantum mechanics, we don't have to do this measurement. We can do any measurement we want. And indeed, in 2016, some very clever people from Singapore figured out that there is an alternative measurement that you can do, namely a measurement in what's known as the Hermite-Gauss modes of the light, for which this Fisher information matrix now, if you look at the separation, this is for estimating the separation, it is independent of the separation. In fact, it's constant. This tells you that no matter how close these two sources are, this measurement will always give you an estimate of the separation, always. Okay, there is no limit. The trouble is that this measurement is very, very finicky. Okay, it only works if you assume that your sources are equally bright, and it requires you to know the center of intensity ahead of time. Okay. So in particular, if you don't know this center, or if you know it, but you don't have perfect control of where you place your device to measure, then you can show that any misalignment, and essentially you get back down to Rayleigh. So this is what this figure shows here. Okay. This is what blows up. So this is the Rayleigh limit. And then this is what happens with the misalignment you have as you get smaller and smaller and smaller misalignment. Okay, but so now you're wondering, okay, but if I don't really need to know, if I'm only interested in estimating the separation of two sources, why do I need to know the centroid? Is there a measurement that allows me to estimate the separation of two sources without having to know this centroid? And the answer is yes. And it uses a very clever effect from quantum optics known as the Hong-Mandel effect. Okay, so you have a mirror, you have the photons entering either side of this mirror, and the Hong-Mandel effect exploits the fact that since photons are bosons, if they're completely indistinguishable, then you know that what you're going to get at the output is both photons are going to go to one detector. You do not know which detector, but both photons will go to one detector. If, on the other hand, the photons are distinguishable in any way, be it their polarization or their spatial profile that is not the same, then you know that sometimes you're going to get the photons landing in different detectors. So when you do the experiment, what you do is you send, for super resolution, for example, you get the photons from two stars, you send them onto the beam splitter, okay, and you count how many times you got coincidences, how many times only one detector clicked versus how many times both detectors click. And that information alone is enough to get you super resolution. And indeed, these are the results from an experiment performed in Poland. Okay, and this is the limit, the standard limit of the optimal measurement if you know the centroid. And what these guys are showing you is, okay, there's experimental errors, is that you can get a finite value, okay, in this case, even if you do this experiment. And in fact, you can even get a pretty good value, even if you assume that your visibility is not that good in the experiment. Okay, now, one thing about this Hong-Mandel effect is that it's very closely related to a very fundamental primitive in quantum information theory known as the swap test. This is a way to answer the following question. I give you two states, and I want to know their overlap. Okay? So this test is not was very famous and known a lot in quantum information theory since a long time. Is essentially what you do is you take the two states, you perform a control swap on them, you throw away the states and measure your control qubit. And this information tells you something about the overlap. Now, it turns out that this test is all well and good, but if I give you n systems, there exists a better test to do to estimate the overlap. Okay, and it has to do with processing the photons in larger and larger batches. And again, the trick is to use these symmetry arguments. So if I give you n photons, all of them in the same state, then if you remember from before, this state can be written in this very special form here. Okay, so now I'm using the total angular momentum to make it more palatable to physicists, essentially. So what you have is the information of what is the total angular momentum of the system, and then inside each sector of total angular momentum, you can ask what is the direction of the systems, okay? Now, if you want to know the overlap of the systems, the only information you really need is the value of the total angular momentum. That is the only information you need, in fact. So this is the measurement you perform, okay? And you will get a precise estimate of the overlap of two states. Well, if you think of the imaging problem that we had, the overlap is exactly what determines the separation of two incoherent point sources. And indeed, in some preliminary results we did with my PhD student, we figured out that if you actually do this measurement, you can approach the same limit that the people who do the measurement based on the centroid get, the more systems you have to measure. Okay, so for example, if you only have two systems, you get this much precision. This, by the way, matches the precision that the experimenters got in Poland. And with 3 systems, you will get a little bit more. And with 4 systems, a little bit more. And if you were capable of taking 50 photons and making this collective measurement, you would hit exactly the same precision as if you measure each one knowing the centroid. Good, and I promise this is the last thing. So I told you a lot about how to use this symmetry to do things that are, let's say, of very practical use. But I'm a physicist at heart, and I'm interested also in foundational problems. And one of the problems I was always interested in is the whole spiel about Schrodinger's cat, or in general, why can we not see macroscopic quantum phenomena on a large scale? So if you look at the laws of quantum theory, there is nothing in them that precludes this phenomena from actually occurring at the macroscopic scale. But we do not see them anywhere, right? And there are several reasons why we do not see them. For example, there is Zurich's famous decoherence or einselection principle, the idea being that, well, large systems are always in interaction with their environment. The environment is constantly measuring you and collapsing your wave function, and therefore you do not see the superpositions. The other explanation is that, well, to see these superpositions, we have to cool things down to 0. We have to have very precise detectors, and human beings are rubbish measurement as detectors. Our eyes are not very good. Our ears are not very good. So this is the reason why we do not see. And the third reason is that, well, when we're dealing with macroscopic systems, well, one has to include gravity in the problem. And so far as I know, there are no theory that unifies quantum theory and gravity. So a lot of people come up with phenomenological amendments to the Schrodinger equation to include the effects of gravity and explain why we cannot see the superpositions. So what I wanted to argue here is that there is an alternative way that you can answer this problem without having to do any of that. The only thing you really need to do is use the invariance of physical laws and standard quantum theory. And here's to give you an intuition of how it works, let's go back to our original example. Here's our 2-level atom, and here's our laser. And if you remember, I told you that, well, if the laser is very big and the system is just 1 qubit, the fidelity is close to 1, right? Okay. So what happens if now your system is comparable in size to the reference system that you have? What happens then? How does this fidelity scale? Okay, so the idea is that this laser here, you can think of it as your measurement device, effectively. It is the reference frame relative to which you're making the measurements. So you can include it as part of your measurement device. Okay? Without it, if you remember, it would be impossible for me to distinguish the superposition from this mixture. If I didn't have this phase reference, these two things are indistinguishable too. And the same thing would happen so the same thing happens with spins and a Stern-Gerlach movement. Okay? So now the question becomes the following. Well, what do you consider a macroscopic quantum phenomena? Well, I take my cue from Richard Feynman, and I said, if I'm able to observe the superposition, no? Or which is the characteristic trait of quantum theory. So how do I do this? Well, I need to see interference. In particular, I want to distinguish the following two states. No, the pure state here, which has these off-diagonal elements, from the mixed state, which does not. This I would consider classical. This I would say is quantum. And this problem is a very, very simple problem of what's known as quantum binary hypothesis testing. I can construct a mathematical formalism that tells me what the optimal measurements is, what is the probability that I can do it. It's very easy. I don't want to bother you with the details. Let's just move ahead. So essentially, if you assume that the state is an equal superposition of two orthogonal states, then the optimal measurements are very easy. They're a projective measurement, and the maximum probability of success for you to distinguish this state from this state in one shot is 3/4. Okay? So now what you say is, you say, okay, what is a macroscopic quantum state? Well, for me, a macroscopic quantum state is a superposition of two states whose invariant quantity, like the energy or the angular momentum, scales with the more systems I add. So for example, a single mode state that is an equal superposition of the vacuum and n photons. Okay, or let's say a spin, collective spin state, which is all spins up and all spins down, for example. That would be a macroscopic superposition. And the goal is to distinguish this state from this state. Okay? And now, if I play the game I played before, I have no restriction on my measurement apparatus, then I can come up with any measurement. But if you remember from the beginning, not everything that is in quantum theory corresponds to a physical thing. So I need to impose a restriction on my measurement device. In particular, the restriction is what I would call a classical measurement apparatus, is that the quantum effects occurring in this measurement apparatus only occur at the individual macroscopic scale. And just like any other classical device, it is reusable. I use it once to measure, and I can use it again and again and again. Okay. So again, the trick, so essentially the way to solve this problem is again to use Schur-Weil duality. You can decompose these states that are constructed into these sectors, and then inside these sectors, you can construct the optimal measurements that you need, and so forth. I won't bore you with the details, but suffice it to say that if you want to do this, in order to achieve the maximum probability of success, which was 3/4, you can prove that the size, in this case, of your laser to distinguish this superposition of 0 and n photons from the mixture will have to be quadratically larger than the actual superposition. Okay, and as a back of the envelope calculation, if you imagine that you have a cat which weighs about 3 kilograms, and that the qubit is really the water molecule in the cat, and that the cat is mostly made out of water, in order to be able to distinguish this macroscopic superposition from the mixture, you will need a Stern-Gerlach magnet whose size will be 50 times the mass of the Earth. So why can't you see superpositions? Because you will need instruments that are extremely huge, and we do not have. So with that, I would like to end my talk and go back to Mr. van der Rohe like I promised you. So this was the statement that symmetry is but aesthetics for fools. And I spent a lot of time trying to find if somebody came up with an equally clever witticism as a response to Mr. van der Rohe. I couldn't find one. So in the end, I ended up inventing one. So this is my nom de plume as a philosopher. And my response to Mr. van der Rohe is that fools are those that reduce symmetry to mere aesthetics. And with that, I'd like to thank you for your attention, and I'm open to any questions you may have.
Thanks, Michalis, for the talk. We have time for a couple of quick questions. Just unmute yourself and ask them. Okay, if we don't have any, I can start with one. And you mentioned before that we have reference frames, right? You wanted to compare these states. So can you include in this formalism some relativistic effects in there?
So yeah, that's okay. So everything I have talked about today doesn't contain any relativistic quantum mechanics. So in principle, that can be done, and there are people, particularly in the group of Czeslaw Bruckner with Giacomo Flamini and so on, that have tried to do the same. So the problem I have, at least in the way that I think about the problem, is that sorry, I think I
Yeah, you have to share as well.
yes, yeah. So the way that we analyze the problem here, the issue is that if you go to non-relativistic reference frames, then you run into the problem where your groups are now essentially not closed and bounded. So your representations are infinite dimensional, and I don't have a very good grasp on how to deal with that aspect of the mathematics yet. It will be interesting to do to see how the things change, but I do not know how to do it. That's the short answer.
Also, you don't have any kind of intuition about open quantum systems, right? This case.
For open quantum systems, I mean, the thing that we have here now is with regards to channels. So you can think of the channels as just the exponentiation of the open quantum system dynamics. But as far as I know, if you impose the symmetry on the master equation itself, on the open system dynamics, then you have a stronger constraint than what I've shown here. So it means that you have more limitations. And I haven't looked at this in particular case at all.
Okay, thank you. Any questions?
I have one question, Michel. Thanks for the talk. It was very nice. So regarding this last comment about the foundations, I mean the measurements, it seems to me that you could phrase it in terms of some constant ratio between. I mean, if you want to measure a spin, you have a Stern-Gerlach if the spin is the electron, but if the spin is a cat, so it has to be like 50 times the Earth. So is there a way to say? I mean, is there a ratio that you have to keep constant or something that I don't know?
So this result here, the way that we constructed it here, it is very closely related to what is known as the Heisenberg limit in quantum metrology. The idea being that what you want to distinguish is states that are very close together, and we know that the fundamental limit here is n squared. So the reason why it comes to be quadratically larger stems ultimately from there. But again, this is, like I said, this is more generally a toy model. So if you impose more realistic constraints, like for example, that your interactions can only follow the inverse squared law, for example, more things like that, then probably you would start getting something which would require even larger and larger and larger systems, probably. Okay.
Thanks.
Okay, so we can conclude the talk. Thanks, Michalis, again for the very nice presentation you've made, and thank you everyone for coming.
Thanks.
Okay, see you. Bye-bye.
Thanks. Goodbye.
Bye.